Swayam Prabha. Digital India. Educated India.
The topic today, as we just left, right, last class was we were talking about the hydrophobic effect, and that's what we are going to discuss today. I'm not sure that we will be covering it in one lecture. I'll at least lead another lecture on hydrophobic effect, right. So, what do we mean by hydrophobic effect, and why is hydrophobic effect so important? So, you can see there are kind of four major points or four major areas where hydrophobic effect actually makes its presence felt. One is molecular recognition between host and guest molecules. So, a large extent of the non-covalent interactions that are involved in such host guest systems has to deal with hydrophobic effect, right, because if there are hydrophobic patches, hydrophobic regions of these two things, then these can enforce this host guest relationship. The second one is the stability of biological membranes. We have membranes, and these membranes are stable, and that stabilization comes because of hydrophobic effect. Next is the topic of this course, which is proteins. Proteins are made up of hydrophobic and hydrophilic parts too, and when you have these tertiary and quaternary structures, a lot has to deal with hydrophobic effect, which ensures that the protein is stable in aqueous solution. And last but not the least, you have heard of surfactants, right, micelle formation, micellization. Weighting, deweighting phenomena, you might not have heard about it, but all these have to do with the concept of hydrophobic effect. Okay. So, this is kind of a few broad areas where hydrophobic effect is important, and that is why someone really should try to understand what hydrophobic effect is from the very first principles. So, let us look at some operational definitions. How do we define hydrophobic effect? See, for us it is very simple, right. When we talk about hydrophobic effect, for example, when we put oil in water, what happens, right? That is an example, a classic example of hydrophobic effect. Oil does not like water, water does not like oil, right. And essentially that is why the solubility of oil like compounds, so hydrocarbons in water, is very low. And that is what we have learned to deal with. That is what hydrophobicity is all about. And the moment we think about it, what we really start also thinking about is that the interactions between your non-polar molecule, or say oil or hydrocarbon, and water are not favorable, and that is why it is better that the oil molecules, they associate amongst themselves, the water molecules, they move apart because of this hydrophobic effect. But is that really true? Do we really need to redefine our thought process with regards to hydrophobic effect? Let us see how we do that. So, just two operational definitions I kind of mentioned right now. One is that hydrocarbons and other nonpolar molecules are very slightly soluble in water, but they show good solubility, right, in non-aqueous solvents. This property is often referred to as hydrophobicity. This is just what we just discussed. Then the second one is the same thing. The low solubility of non-polar groups in water can lead to their aggregation, as seen in protein folding and micellization. So, micellization we know, when micelles form, these things come together, and if these are micelles, then they have their polar head groups which point out and the hydrophobic tails which point inside. And you can also have micelles in the inverted form, that is reverse micelles, where if your bulk is an organic solvent, then your hydrophobic tails would be pointing outside and your polar head groups would be pointing inside. So, these are reverse micelles, but anyway hydrophobic effect is dominant in both the cases. So, how do we relate it to proteins? When a protein folds, obviously this we have discussed also, the hydrophobic amino acids will have to move to the interior, because simply speaking hydrophobic amino acids do not like water. Hence, as has been said here, hydrophobic interaction can be associated with the process by which a hydrophobic side chain of an unfolded protein is removed from water and buried in the protein interior. You know, that is essentially what you are doing, right. When a protein is synthesized, it is mostly linear, though with some shades of structure depending upon the protein sequence or the type of protein that we have discussed before. But there will be many hydrophobic amino acids which would not be in the form of a structure, they would not like water. So, essentially when you go from the folded to the unfolded form, what you do is, if you would be doing it, you would just take that hydrophobic amino acid side chain, take it out from water and put it inside the protein core, because that protein core is shielded from the bulk solvent or water molecules. That is essentially what you are doing, right. And this is the connection between hydrophobic effect as you know, or as defined, or as we think, and protein folding. Now, Walter Kaufmann, as I was telling you briefly yesterday, he came up with a brilliant idea. What he said was, he proposed a solvent transfer model. What do I mean by that? That means a solvent transfer model by which the aforesaid chain burial process means where you are burying the hydrophobic amino acid side chain when your protein is folding into the protein core. This can be modeled by the partitioning of a model compound between water and a non-aqueous solvent. The same thing. That means you have different R groups, different hydrophobic R groups. So, with relation to that R, whatever R is, if you would be able to take a compound which closely resembles that R, that hydrophobic moiety, and what you just look at is the partitioning between an organic phase and the water phase, because that is essentially what you are doing. You are looking at the relative solubilities. So, he defined something known as a standard free energy change, or this is called standard energy of transfer, but let us stick to this right now. The standard free energy change delta G 0, right, for dissolving toluene in water can serve, there is a mistake, it should be can serve as a model to estimate the burial of a phenylalanine side chain. Now, you have to reason out why I can take toluene as model for the phenylalanine side chain, but it can be taken. And if I would look at the thermodynamics of this transfer or partitioning of toluene in water and another organic solvent, I would get an idea of the energetics that would be involved if I would take a phenylalanine side chain in water and put it in an organic solvent. In this case, the organic solvent being what? The protein core, because the protein core essentially is hydrophobic, right, polarity is very low. So, that is why it is called the solvent transfer model. That means, you try to model the energetics involved in protein folding in real life by taking very simple model compounds. That is essentially the idea. Now, so as I was talking about solubility, the standard Gibbs energy of transfer, right, transfer can be expressed as follows, where delta G 0 is equal to minus RT ln x, x being the mole fraction of hydrocarbon dissolved in water. It is a bottom line, it is very simple. Now, let us consider some questions. The moment you think about this transfer model and the moment you think about trying to take a model compound which will serve as an ideal model for any hydrophobic amino acid side chain, the first question that come to your mind is, or will come to your mind is, how do I choose a suitable solute, right? Because I have to choose someone which is, say, structurally almost identical, or if not identical, very similar to that hydrophobic amino acid side chain. Otherwise, if that is not the case, then the energetics involved will not match, we cannot compare. So, that is the first question that comes, which solute can accurately model the transfer free energy of a non-polar amino acid side chain? That is the first question. Now, not only that, again, because we are talking about a transfer model, that means from water to a non-aqueous solvent or non-aqueous solvent to water, whichever you try to look at it, which solvent would be best suited to model what? The interior of the protein, because we know that the interior of the protein is non-polar, but then would there be any particular solvent which can best suit our needs for trying to model the protein interior? That is the second question, right? You see, these are very logical questions if you think about a person trying to understand from the hydrophobic point of view how a protein folds, right. And the third is, the moment you have taken this and put it in a hydrophobic interior, or the moment you have taken a non-polar chain and put it in water, what are the different interactions involved? Essentially van der Waals interactions involved, and this is something we have talked about at some length, especially in the last class, where we said that typically your dispersion forces are modeled with the use of the Lennard-Jones potential, right. So, the last point is how to model the van der Waals interaction of the non-polar side chains in the protein interior, and this aspect we have looked at already through the Lennard-Jones potential, we know that. Now, let us go one step forward. Is there any relation between hydrophobic effect and surface area? Now, there are two ways of looking at it. So, what you can see is, in the middle, if you look at this, in the middle is your hydrophobic molecule. Okay. These spheres which are resembled by S or which are represented by S are essentially a solvent phase. Now, think about this, we refer to something, if you kind of recall, there was something known as hard phase potential, right. So, here what we are saying is that solvents can be modeled as hard phase, right. That is just an approximation. But the most important point is, if you look at this solid line, what does it say? What it says is that the center of this solvent molecule or any such solvent molecule will not be able to go beyond the solid line. That means, whatever area is out here is the one which at the most will be accessible based on the hydrophobic molecule which I have in the center. Anything beyond that will not be accessible, or vice versa. If this is my hydrophobic molecule which is in the center, then this is the area which it makes accessible to the solvent molecules which are, or which it is immersed in. Is that clear? So, that is why this term is very important, accessible surface area. That means, accessible means the ones or the surface area that can actually be accessed by the solvent molecules as shown by this schematic. Okay. So, as it says, S is representing the solvent sphere, and I have taken it for this reference. The other way of looking at it is, see here we drew the line through the center. Here this is referred to as a molecular surface. That means, what we do is we take it right along the surface of the molecule, we do not take it to the centers of the solvent molecules, right, and hence it is referred to as a molecular surface. But the idea essentially is the same. You are looking at the accessibility of the solvent molecule to the respective hydrophobic molecule which you have put inside the solvent, right. Let us look at some relations or a tabular in the tabular form. So, what happens? Remember, delta G0 is your transfer free energy, right. We are looking at a host of alkane molecules, right, and then in the second column what you are given is your accessible surface area. That is what you are being provided with. Now, see, this is no brainer. As we go from methane to decane, obviously the chain length is increasing, right, and if the chain length is increasing, then accessible surface area has to go up. So, that is exactly what is happening, right. I have intentionally omitted some other alkanes in between, just so that it fit here, but I guess it drives home the point. And you look at delta G 0, remember delta G 0 is a transfer free energy, and obviously the more is the surface area, right, the more will be the transfer free energy. Simple, because there will be more interaction, either favorable or unfavorable, does not matter what it is, but there will be more surface area. That means more solvent molecules can come close to the hydrophobic molecule. That means there is more accessible surface area. So, if you would plot it, so suppose you are given this and you would plot delta G 0 on the y axis versus the accessible surface area, what would you get? And there is a very good result. What you get is your transfer free energy essentially is almost a linear function of your accessible surface area. Now, what does it mean? It tells you a very simple thing. The transfer free energy is what? A parameter which is giving you an idea about how hydrophobic that corresponding molecule is, and one immediate effect or one immediate connection you can make is that the higher the accessible surface area, the more will be delta G 0. That means the more should be the hydrophobic effect being felt in the system. So, based on this, what we can write is, now I will use the sheet. We can write delta G 0, this is my transfer energy, right, delta G 0 is equal to kh times say the accessible surface area, kh times accessible surface area. That's what you saw, right, because the plot was actually passing through the origin, there was no intercept. So, I can easily write this. So, this is a certain proportionality constant, let us not worry about the details too much. Now, how can I relate it to a protein which is folding? So, what I can say is, for a protein I can write delta G 0 is equal to k h, again the proportionality constant. Now, I can write this, let me write it, kh times accessible surface area of the native state minus accessible surface area of the unfolded state, right. So, N stands for native state of the protein and U obviously is the unfolded state of the protein. K being a proportionally constant, that depends upon other factors, but let us not worry about those specifics. But think about this, we started with this hydrophobic effect, we looked at its relation with accessible surface area, and then there is an immediate connection, because when you are going to open a protein up or when you are going to fold a protein, there would be a change in the accessible surface area, right, to the solvent molecules, and that would be a direct relation to your transfer free energy, that is direct relation. Now, the question is, if I look at this initial equation delta G 0 is equal to k h times the accessible surface area, do you think it will always hold? That is the question, right. What do you think? Any ideas? What was very special about the molecules we had considered the accessible surface area of? What did we consider? We considered methane, ethane, propane, butane, right, up to decane, right. So, all those were linear chain alkenes, right. So, now the question is, how far is the linearity of the relationship between the transfer free energy delta Z 0 and accessible surface area valid. That is the question we are trying to answer. To make the point, thus far we had only considered linear alkanes. We had only considered linear alkanes. However, think about this. If you go to very long chain alkanes, what happens is these alkanes have a tendency to curl up or fold onto themselves. And the reason is very straightforward. If the alkane chain is very long, the accessible surface area will be huge, but the alkane chain would not be liking to interact with water molecules, right. But because the alkane chain is very long, instead what it can do is it can try to bring other parts of its chain closer to itself, and the moment it does, there can be a certain sort of collapse in the structure, and that collapse will give rise to this curling or folding in some sense, because it has to minimize the so called unfavorable interactions with the water molecules. That is essentially what it has to do. And so this was one, and the other one is what if you have branched alkanes? What if you have branched alkanes? If you have branched alkanes, then you know, depending upon the branching, your accessible surface area will vary, right. And then there is no necessity that your delta G should exactly track as your accessible surface area, that is, maintain the linear relationship. So, that means 1 and 2 together, so 1 plus 2 either or together can make your plot non-linear, And just to be specific a little bit, what I showed you in the previous sheet, in one of the previous sheets, I can refer to this as delta G0 hydration, and same here, because essentially we are looking at the interactions of this non-polar hydrocarbon with water molecules, and hence hydration. Okay. So, what we already have is one measure of hydrophobicity, which is your accessible surface area. Now, keep that in mind. What about the molecular nature of hydrophobicity? For example, if you would try to model a solvation process, that means you take a molecule. So, we are looking at the molecular nature of hydrophobicity now. So, for example, you have a hydrophobic molecule, right. So, this is a hydrophobic molecule, right. This is a hydrophobic molecule H, right. When you have a hydrophobic molecule H, and suppose you have a series of water molecules out here. They are all your open circles. So, this is water, and what you have to do is you have to take this and put it inside. Again, what you are essentially doing is you are inserting H, which is a hydrophobic molecule, into water. Now, think about the process very carefully. What do you think is going to happen? See, the first, see, it is very logical, right? I am taking a hydrophobic molecule H, I am trying to pour it in water, because I have to look at the corresponding energetics, right. Now, if I have to try to take this H and pour it in water, the first thing I have to do is I have to be able to make a cavity, because I have to place that hydrophobic molecule in water. That means, I have to find a cavity where the hydrophobic molecule will go and move the water molecules out from there. Hence, this insertion or this solvation can be considered to be a two-step model. So, that means, I can write this insertion or solvation can be considered to be a two-step process. What is the first step? The fourth step. So, in the first step, what happens is thermal fluctuations in the solvent, which in this case is water, will give rise to cavity formation, will give rise to cavity formation. Okay. And let this process be reflected by the thermodynamic parameter, say delta G c, right. There is the first step. Now, what do you think will the logical second step be? You have already produced a cavity. See, how is the cavity being produced? Because you know you have thermal fluctuations. Because of thermal fluctuations, the molecules will be fluctuating, and it is like an instantaneous dipole. It instantaneously gives rise to cavities. Once it gives cavity, if you have the hydrophobe, that you stick that hydrophobe or hydrophobic molecule into the cavity, which is H, the hydrophobic molecule. What is the second step? If the hydrophobic molecule has to stay in the cavity, it has to start interacting with the surrounding solvent molecules, right, which in this case is water. So, the second step can be thought about like this. So, this is the second step. The solute, which is the hydrophobic solute, which is H, enters the cavity. The solute H enters the cavity, and van der Waals interactions come into play between H and the solvent molecules. Between H and the solvent molecule. So, essentially here what happens is solvent molecules reorient themselves on the surface of the cavity produced by insertion of H, which is a hydrophobic molecule. And what we say is this energetics, this van der Waals interactions we refer to as EA. The van der Waals interactions we refer to as EA. So, I have two components. What are the two components? One is delta Gc, which is the energetics involved in cavity formation, and the second is your van der Waals interactions, because after it is there, it starts interacting with the surrounding soluble molecules. See, if you think about it, the way people devised models of trying to look at hydrophobicity or hydrophobic effect. So, this is a very logical way of looking at it, right, and it is nothing unique, it is nothing out of the blue, it is just that you have to be able to think like this, you have to be able to design your problem like this. It is not hard, right. I mean, these are two very logical ways of looking at it, at a solvation. So, what we can do now is we can combine these two processes and say that then my delta G0, which is my transfer, is a combination of delta Gc and EA. Remember, this one is a transfer free energy. There is a transfer free energy, that is what we had looked at before. So, whether this transfer is favorable or not favorable is dictated by two terms, delta Gc and EA. Now, remember, if you think about what we know with regards to hydrophobic effect, this EA is the one we think is the main culprit, right, because your interaction between a hydrophobic molecule and water based on just regular solutions, right, regular hydrophobes in oil in water, is EA should be the culprit, right. The EA is the one because your interactions are not favorable at all, and that is the one which should actually make delta G positive, that is the transfer not favorable, right. That is simply what we want to think like, and that is what I do not know about you, but at least that is what I have been thinking about it, the way I have been thinking about it. Okay. But is that true? Let us look at a table, but before the table let us look at this figure. This figure is referred to as the free energy of cavity formation. Now, what does it mean? If you look at the figure, I have plotted this delta Gc. Remember what I said, delta Gc is the free energy with relation to cavity formation, and what do you have on the x axis is accessible surface area. This is something we know by now, right, what accessible surface area means. Now, this solid circles or the filled circles are for certain organic molecules in water, and the open squares are for the same organic molecules in a liquid alkene. Okay. I am not telling you what the molecules are, I will tell you what those are in the next slide, right, where I actually give you the table. But look at this, what is very surprising, maybe what we have not thought about it before, maybe this would encourage us to think like this. You look at the cavity formation free energy, where is it more? Is it more in alkenes or is it more in water? It is always, it is more in water, right. Okay. Now, this is something we never thought about. That means I am trying to produce a cavity in water and I am expending so much more energy than I can do in alkenes. But see, I am not even talking about interactions now, I am not even talking about interactions, I am just talking about trying to separate the soluble molecules so that I can bring the hydrophobic molecules inside, or molecule inside rather, if you get one molecule. Okay. And because this is plotted against accessible surface area, you can understand. So, as we are going from left to right or from low surface accessible surface area to higher accessible surface area, it means I am essentially increasing the chain length of my organic molecule or hydrophobic molecule. So, the main conclusion is of the previous slide or the figure, the work of making a cavity in water is much larger as compared to that in liquid alkanes. Okay, that we know by now. Now, let us look at the table. So, what was the solute? You look at the solute respectively was first propane, then isobutane, then neopentane, right. So, this was the solute which you dissolved in water, then you took the same solutes and you dissolved it in the corresponding alkane. See, you know, propane, you take propane and you dissolve it in propane, you take propane and you dissolve it in water. Similarly, you take isobutane, you dissolve it in isobutane, you take isobutane and then you dissolve it in water and you compare the energetics, that is what you are doing. The same for neopentane. So, look at this delta Gc, right. The moment you go to water, you typically from propane to neopentane, the delta Gc is increasing. Now, this is expected based on surface area, accessible surface area, and that is what we saw in that figure. The table is the picture is based on this or the figure. If you go to liquid alkane now, you know the same thing happens, but here what you can see is delta Gc is immediately lower than that in case of water, but still it is positive because you are having to insert it inside the solvent and you are having to do work, that means you are spending energy. So, it is positive. Okay. Now, let us not worry about the enthalpy of the cavity. You look at the entropy. Okay. Do not worry the enthalpy right now. What is the biggest difference? You think when I take propane, right? When I take propane, I put it in water, and if I take the same molecule and I put it in the corresponding liquid alkane, you can see that delta S in all cases for liquid alkane is positive, and that corresponds to a negative delta G, right, because it is minus T delta S. But for all cases in water, that delta S is what? Negative, or T delta S is negative. That is what you are plotting essentially, which will correspond to what? Positive free energy, right, because this will give a positive contribution to your Gibbs-Helmholtz equation. But see, again we have not talked about energetics. This is just a entropy formation with relation to what? The cavity. Okay. Now, look at the last column. Isn't it surprising? What is your last column? Your last column is essentially a van der Waals interactions. The interactions we have so far thought to be absolutely unfavorable between what? Between your hydrophobic molecule and your solvent molecules, which is water in this case. But do you see much of a difference? Essentially, the EA, if you go to water and you go to liquid alkane, they are negative in both the cases, and they are almost of similar magnitude. So, we might have to redefine or recalibrate our thoughts with respect to hydrophobicity. It is not your EA, it is not your unfavorable interaction, it is something else. It is coming from your delta Gc, where the major culprit is what? Entropy, because you look at enthalpy. Enthalpy in both the cases is positive. Can you look at the you look at delta Hc, in both the cases your enthalpy is positive, right. So, there is no distinction. What happens is what is the actual determinant is your entropy. That is the one which makes the free energy of cavity formation in water so high. It is not your EA, please, again it is not your EA, it is not your van der Waals interactions. Is it clear? Okay. So, all these were done at 25 degrees Celsius, you have to do it at a fixed temperature obviously. So, just to kind of look at the observations again from the previous slide. If you take neopentane, the delta Gc is 46.5 kilojoules per mole, and if you would, so neopentane in water, and if you take the neopentane, same neopentane, and put it in liquid neopentane, what would delta Gc be? 27.6 kilojoules per mole, right. And we have defined EA. EA is the work involved in solvent reorganization when the solute enters and becomes a part of the cavity. That is how we have defined EA to be. Now, from the table, EA has similar values for all the solutes. Okay, that is what we just discussed. So, what is the implication? The implication is, again we were discussing that the van der Waals interaction energy is similar for both water and the alkenes. This is, do not you think it is surprising? Don't you think it is surprising with respect to what we have been thinking all these days with regards to hydrophobicity? Or maybe you have been thinking about cavity, I do not know, but I think it is a different way of looking at it. So, the next question is, see, I am not worried about EA anymore. Why? Because they were very similar. So, the only thing I need to worry about is delta GC. So, then the next question that comes to your mind is, why is the work of making a cavity in water so large? Why do you have to spend so much more energy in trying to make a cavity in water as corresponding to an alkane, right? The first reason is the small size of the water molecule. Now, what will happen if you have a small size? If you happen to have a small size, and if you can just try to give you a schematic, if the size is very small, suppose these are water molecules, if the size is very small, okay, this is the small size of water molecules. If the size is very small, what would it lead to? It would lead to high packing density, isn't it? It would lead to high packing density, that is smaller void volumes, which is essentially your cavities. So, this one is clear to you. If the size is small, they would pack a lot more densely, and hence because the packing density is very high, the number of gaps or void spaces would be very low. So, definitely to take a hydrophobic molecule and put it inside, you have to put in more work, put in more energy in creating a cavity, as opposed to large spherical particles. So, if you have large particles like this, if your particles would be large, they would come close, but they would leave many huge voids. Okay. So, large particles, if they are large particles, we can write high void volumes. Okay, so it is the small size of the water. So, this can be explained by a theory known as scaled particle theory. We will not worry about it, but what scaled particle theory essentially says is, work is required to exclude the centers of molecules from any specified region of space in a fluid, that is, it is an excluded volume effect. What it means is, suppose you have a hydrophobic molecule here and you have water molecules here, right? You have water molecules here, and this is your H. So, this was your initial, this was your initial, and you took the hydrophobic molecule and put it inside the water. You have to create a cavity. Now, when the cavity was not there for the hydrophobic molecule, what did you have? You essentially had water molecules out there. So, for example, if you are sitting there or if you are standing there, and if I go and try to occupy your place or your space, I will not be able to, because that volume is excluded to me. The only way I can do it is if I push you out of there. The same thing has to be done by the hydrophobic molecule. Initially, when there was no hydrophobic molecule, all the water molecules were covering all space of your container or wherever. Now, the moment you try to put in the hydrophobic molecule, you have to move water molecules out. That means the water molecule was excluding some volume, and you have to make sure that it is moved out, so that you can place the hydrophobic molecule in. Okay. So, what we can say is, in other words, if a solid molecule is placed in a solvent, a huge number of solvent configurations that were available in the pure state on the solvent become unavailable. Now, is this clear? See, for water we know you have extensive hydrogen bonding, extensive ordering, right. Now, the moment you put in a hydrophobic molecule, do not worry about hydrogen bonds now. What happens is that space is not available to the water molecules, right. So, immediately what would happen is, because that is excluded volume to the water molecules, the volume excluded by the hydrophobic molecule, it cannot occupy that place. That means it cannot occupy, it cannot have certain orientations. The moment it cannot have certain orientations, what are you doing? You are actually decreasing the number of microstates, as you have done in statistical thermodynamics. Essentially what you are doing, you are decreasing the entropy, you are essentially decreasing the entropy. And remember, what was delta S in that table? T delta S was negative, which corresponds to this, right, the entropy being negative. So this therefore results in a reduction in the number of configurations, and hence is accompanied by decrease in entropy. So now you can imagine that this hydrophobic effect, what we know by name, might essentially be an entropic effect rather than your EA, rather than your van der Waals interactions. Now what is the other way of looking at it? So this is one, the small size of the solute. The other one is something known as cohesive energy density. Now what do you mean by that? See, water has a very high cohesive density, energy density. What do you mean is, see, water has extensive hydrogen bonds, they like each other. So that means the cohesion force, that means these water molecules to stay together, the ability is very high. So cohesion means cohesive forces, right, they like to stay together. So the cohesive energy density, which is the CED, is the overall molecular cohesion of a liquid. It is given by the total change in energy of the solvent from a liquid to a non-interacting vapor at 0 pressure. What do I mean 0 pressure? Why is 0 pressure so important? Can someone tell me why is 0 pressure so important? See, I am taking this and moving the solvent from the liquid to a non-interacting vapor. It is ideal gas. When can you expect gases to behave ideally? When pressure is very low, tending to 0 pressure. That is what we are trying to put in, okay, which can be represented by the change in internal energy or the change of vaporization, as C, which is your cohesive energy density, is given by the change in vaporization internal energy over Vm, which is the molar volume of the corresponding solvent, and you know H is equal to U plus PV. From there I can write that delta U is equal to delta vaporization H or delta H vaporization minus RT over Vm. Keeping in mind, because it is 0 pressure, PV is equal to nRT, my ideal gas law is valid, right. So you can immediately understand water is one of the liquids having the highest what, delta H vaporization. Also water is one of the liquids having a very small Vm. So these things in combination make the cohesive energy density to be very high, right. So as I said, CED of water is by far the largest among all common solvents, and as a consequence of both the strength of hydrogen bonds and the smallness of the molar volume of water, right, that is what it is. Your delta H vaporization depends upon the strength of the hydrogen bonds. The more hydrogen bonds you have, the more energy you need to break the hydrogen bonds and try to vaporize them. So delta H vaporization is higher, and also the molar volume is low. The molar volume was in the denominator, so if it is low, obviously then the C factor increases. So hence you are looking at two effects now. One is the CED, you can understand, which is enthalpic in origin, right, because you have delta H, and the other one is what, this scale particle theory, which is the size, which is essentially what, entropic in origin. Well, then the obvious question is, which one is more instrumental, right, which one dominates, or which one is more important. Okay, we will look at that later, but let us look into some thermodynamics. I will just start with this, and then in the next class I will elaborate on it more. See, what you are looking at are two very interesting figures. What we are going to discuss now is temperature dependence of hydrophobic interaction, okay, that means how this varies as a function of temperature, obviously, and here what you are looking at is the mixing thermodynamics of this organic molecule neopentane. So look at your left and right figures, or the first figure which says neat phase to water means you are taking neopentane in the neat phase, that means neopentane is a neopentane, that is a neat phase, liquid phase. You take a neopentane molecule out and you put it in water, and this is the corresponding thermodynamics. The right panel, what does it show? It tells you that you are taking a neopentane molecule now. See, it does not make sense to take a neopentane molecule out of neopentane and put it back in neopentane again, right. So, what it tells you is you take a neopentane molecule in the gas state, vapor state, and then put it in neopentane itself. That is why it says gas phase to neat phase, that means neopentane gas phase to neopentane liquid phase, and the other one was neopentane liquid to neopentane in water. Is it clear? Now, what is delta mu 0, delta H 0, delta S 0? You know what it is. Now, delta mu is essentially a chemical potential. Now, we are talking about chemical potential. Remember, the chemical potential essentially is an escaping tendency or gives you an idea of how probable is this, or what is the potential of this occurring. What I mean by this is solubility essentially, right. So, here I have delta u 0 or mu 0 rather, and then I have the corresponding delta H 0, the enthalpy 0 referring to the standard state, and delta S 0, this is entropy. Again, let us not worry exactly what they mean, but just look at it. Look at the left figure where we say neat phase, that means neopentane is taken from liquid to water. How does the delta mu 0 vary? First of all, this delta mu 0 is positive, right, and it should be positive. Why? Because it is not favorable to take neopentane and dissolve it in water. Your delta G obviously would be positive, there is no doubt about that. But look, it is not a straight line. As you increase the temperature, which is temperature is on your x axis, you see it goes to a certain curvature, that means it has a temperature dependence. Okay. Good, is that clear? Now, look at these, the dotted line and the dashed line and the dotted line. So, the dashed line is the one which says delta H 0 and the dotted line is the one which says T delta S 0. Okay. You see these have extensive slopes, these have extensive slopes, right. They are not just lines parallel to the x axis. Now, tell me what is the slope of delta H over temperature? That means, if I have d of delta H 0 over d of T, what is that equal to? Very good, it is not Cp, it is actually delta Cp, because Cp is equal to dH over d of T, and d of del H over d of T would be delta Cp. What does it mean? What it means is, the only way I can have a big slope is that my delta Cp, that is the change in heat capacity, is huge, right, because that is what the slope is. Same thing for T delta S. You know what the relation between entropy and heat capacity is? You know what it is? Look it up, we will do it next class, but there also this d of del S over del of T would be having a Cp dependence, delta Cp dependence. So, the change in heat capacity is huge, and that is why you have a slope for both delta H and delta S. Now, please keep this in mind. You go to the next one, that means the right figure. Here you can see delta mu 0 is negative. Now, this is expected, right. If you are taking neopentane and put it in neopentane liquid, it has to be negative, because it is a favorable process, spontaneous process. Now, not only that, see both T delta S 0 and delta H 0, these lines, they have slopes, they have certain curvatures, but is the slope as evident as the one you see in the left figure? No. What does it mean? It means that the change in heat capacity in case of taking neopentane from gas phase to neopentane is very small, as compared to the same change in heat capacity when you take neopentane from neat neopentane to water. Okay. So, heat capacity change is actually the one which to a huge extent defines your hydrophobicity, right, and this is something we will try to develop in the next class. Okay. This is really unique, the way you look at it, it is really unique, and I will tell you one thing just before ending. you look at this TH and TS, see what happens at TH. What is happening at TH is here this delta H line is crossing this 0 free energy, right. So, what it means, or 0 energy kilojoule per mole, I mean what it means is at this your delta H 0 is equal to what? 0, right, because that is the 0 line. So, this line is the 0 line, right, this line is 0 line. You see there is a line in the middle which is 0 line. So, when the delta H 0 crosses that line, that means it is 0, and that occurs at a certain temperature. So, that is TH, there is TH is that temperature where delta H 0 is equal to 0. Similarly, if you go over to the higher temperature side, what happens? You can see the entropy line T delta S 0 crosses 0 at this temperature Ts. So, Ts is defined as that temperature where the delta H 0 goes to 0. So, now guys, you think about this, on the left side lower temperature your enthalpy is 0, right, your delta H 0 is 0, right, at the lower temperature your delta H 0 is 0. Hence, your contribution to delta H is what, essentially what, entropic or enthalpic? Entropic. And you move to higher temperatures, what happens? Your delta H 0 now becomes 0. So, your contribution now becomes essentially what? Enthalpic. So, when you look at the temperature dependence, you actually do a change from parameter dependencies. That means, you do a change from entropy dependence to what? You go to enthalpy dependence, and that is something which is extremely interesting. We will try to look at this in little more details in the next class.